Lecture number 1.21, Relationship between specific heats. The problem statement is like this. For an ideal gas, so that Cp minus Cv is equal to capital R, where all the terms have usual meaning. Cp is specific heat at constant pressure, Cv is specific heat at constant volume, and capital R is characteristic gas constant. Or, for an ideal gas, establish the relationship between Cp, Cv and R. In order to establish the relationship between Cp, Cv and R, let us consider a gas enclosed in a container and being heated at constant pressure. Because of this heating, the gas undergoes change of state from 1 to state 2. As shown in the figure, there is a container comprising of control volume and control surface. It is containing a gas of known mass m. It is heated, and because of this heated, the gas expands and piston moves in the upward direction such that pressure always remains constant. However, volume may get changed. So this figure represents heating of an ideal gas at constant pressure. Let small m is equal to mass of the gas being heated in kilogram, capital T1 initial temperature of the gas in Kelvin, capital T2 final temperature of the gas in Kelvin, capital V1 initial volume of the gas in meter cube, V2 final volume of the gas in meter cube, Cp specific heat at constant pressure in joule per kg Kelvin, Cv specific heat at constant volume joule per kg Kelvin, and small p is constant pressure of the gas in Newton per meter square or in Pascal. Since the gas is heated at constant pressure, so heat supplied at constant pressure during change of state from 1 to state 2, or I can also say during process 1 to 2. Now, while discussing a specific heat at constant pressure and a specific heat at constant volume, we know that heat supplied to the gas during any process at constant pressure is equal to change in enthalpy, and this can be calculated as mCp T2 minus T1. Let's say this is equation number 1. Now what happens when the gas is heated at constant pressure and heat is supplied at constant pressure? Some of the heat is being utilized in doing external work, and rest of the heat remains within the gas and is used in increasing the internal energy of the gas. So I can say heat supplied at constant pressure has two components. One is utilized to do useful work, and remaining is utilized to increase in the internal energy. So therefore heat utilized for doing external work so work done during the constant pressure is given by P into V2 minus V1. And heat utilized in increase in internal energy can be given by the equation delta U1 to 2 is equal to mCv T2 minus T1. Let's say this is equation number 3. Now the gas is undergoing a process 1 to 2. So I can apply first law for a system, particularly closed system, because in our case the gas is heated in a closed container, so it will be treated as a closed system. So applying first law for a closed system undergoing a process 1 to 2, and what is the first law for a process? Q1 to 2 is equal to change in total energy plus work done. Now change in total energy can be given as change of internal energy plus change of kinetic energy plus change of potential energy. In this case, change in kinetic energy is 0, as no change in velocity of the system, no change in velocity of the system because it is stationary. During the heating, the closed system is not moving. And its potential energy is also 0 because datum is fixed. So what happens under this condition? Let's say this is equation number 4. So under such condition, change in total energy will be equal to change in internal energy. So equation 4 becomes Q1 to 2 is equal to delta U122 plus W122. Now this is the first law applied to the heating process 1 to 2. Now in this equation, from equation 1, 2 and 3, putting the values of Q12, delta U12 and W12. So it becomes MCP T2 minus T1 is equal to MCV T2 minus T1 plus P into V2 minus V1. Let us say this is equation number 5. Now writing characteristics gas equation, that is PV is equal to small mRT. So for state 1, I can write characteristic gas equation as P1 V1 is equal to mRT1, and for state 2 I can write it as P2 V2 is equal to mRT2. Therefore P1 sorry P2 V2 minus P1 V1 is equal to mR T2 minus T1. Here pressure is constant, so I can take pressure as a constant value. P V2 minus V1 is equal to mR T2 minus T1. P1 is equal to P2 is equal to P. Let's say this is equation number 6. So from equation 5 and 6, putting the value of P into V2 minus V1 is equal to MR T2 minus T1, it will be MCP T2 minus T1 is equal to MCV T2 minus T1 plus M capital R T2 minus T1. Now here M and T2 minus T1 are common, so they will get cancelled out, and remaining term will be Cp is equal to Cv plus R, or I can also write it as Cp minus Cv is equal to R. So this is the relationship between Cp, Cv and R. For molar specific heat, this relations can be written as Cpm minus CVM is equal to RU, where RU is universal gas constant. So if I am considering capital R as characteristic gas constant, the relationship between Cp and Cv will be Cp minus Cv is equal to capital R. And if I am considering molar specific heat, the relation becomes Cpm minus Cpvm is equal to Re, where Cpm is molar specific heat at constant pressure and Cvm molar specific heat at constant volume, and Ru is universal gas constant. Now one more relationship I can find out. Ratio of specific heat. Now the ratio of two specific heat Cp over Cv of a gas is an important constant in the field of thermodynamics and is represented by a Greek letter gamma, and it is called as adiabatic index. Now since value of Cp is always greater than value of Cv, therefore value of adiabatic index is always greater than 1. So this is another relationship between Cp and Cv in terms of adiabatic index gamma. So let us try to find out two more relationships for Cp and Cv. Now just now I have derived Cp minus Cv is equal to R, and I have the relationship gamma is equal to Cp by Cv. So Cp by Cv minus 1 is equal to R by Cv. I can put the value of Cp by Cv as gamma minus 1 is equal to R over Cv. So from here I can find out one more relationship expression for Cv as R over gamma minus 1. So I can also find out the value of Cv in terms of characteristic gas constant R and adiabatic index gamma. Similarly, gamma is equal to Cp by Cv. So Cp will be gamma into Cv, or Cp is equal to gamma R over gamma minus 1. So this is another expression to calculate the value of Cp in terms of gamma and characteristic gas constant R. So with this I come to an end of this lecture. Happy learning.